T9.12. A random sample of 100 of last year's model of a certain popular car found that 20 had a specific minor defect in the brakes. The automaker adjusted the production process to try to reduce the proportion of cars with the brake problem. A random sample of 350 of this year's model found that 50 had the minor brake defect. Was the company's adjustment successful? Carry out an appropriate test using alpha 0.05 to support your answer. All right, so let's just write some things down. So last year we had 100, 20 had the defect. This year it's 350 and 50 had the defect. Okay, so let's write N1 equals 100, X1 equals 20, so P hat 1 equals 0.20. And then we can write, let's do it over here, N2 equals 350, X2 equals 50, P hat 2 is equal to 50 over 350, 0.143. And because this is a two-sample procedure, we are going to have to use the combined proportion to check the large counts and to calculate the test statistic. So that's going to be 20 plus 50, or 70, divided by 100 plus 350, which is 450. Okay, so 70 out of 450 is 0.156. That was rounded. All right, so let's go through the 4C method. So the first step is to choose the procedure. This is a two-sample z-test for a difference in two proportions, P1 minus P2. Okay, P1 minus P2 is our parameter, which represents the true difference in the proportions of cars with the brake defect. And this is last year minus this year. Okay, last year minus this year. Okay, our null hypothesis is that there is no difference, so P1 minus P2 equals 0. The alternative hypothesis has to be consistent with this statement here, that they've reduced the proportion of cars with the brake problem. So that would mean that this year's car has a lower proportion than last year's car, right? So P1 minus P2 would be greater than 0, right? Another way of saying it is last year's car has a higher proportion of the defects than this year's car. Okay, what else do we need to do? Significance level, 0.05, statistic. So P hat 1 minus P hat 2, that's 0.20 times 0.143. So 0.057. Okay, and so right now, this does give us some evidence for the alternative, because the difference in the sample proportions is greater than 0. Okay? But we always have to check, is it convincing evidence? Is it significantly greater than 0? Okay. All right, check step. Okay, so we have random samples. Yes, so we see the word random right here and random right there, and they were taken independent of each other. I mean, happened in different years. So we can say independent random samples. Check. All right. Now, we're going to assume that 100 cars is less than 10% of all cars from last year, and that 350 is less than 10% of all cars from this year. Okay. Now, if it's a big auto manufacturer like Ford or Toyota or whatnot, like they're making hundreds of thousands of cars every year. All right, now let's check the large counts condition. So be careful here. We need to use the combined proportion when we check the large counts. So this will be 100 times 0.156, 100 times 0.844, I think. And then we'll do 350 times 0.156 and 350 times 0.844. Okay. If you don't mind, I'm just going to calculate these off screen. Well, actually, the ones with 100 are easy to do. All right, that's 15.6 and 84.4. 350 times 0.156, 54.6. And then the other one would be 295.4. Okay, all right, and all of those values are at least 10. All right, so let's start with our general formula, right? Standardized test statistic, pardon my abbreviation. It's a statistic minus a parameter divided by an SD. All right, and so the specific formula, so our statistic is this notation here, p hat 1 minus p hat 2. Our parameter is this notation here, p1 minus p2, and then the SD is that long square root expression. Okay. p hat 1 minus p hat 2 minus p1 minus p2 over the square root. And this is where we need to be careful again, because we're going to use the combined proportion when we write out the SD. P hat c 1 minus p hat c over n1, p hat c 1 minus p hat c all over n2. All right, now we can start plugging in the numbers. Okay, so our statistic was 0.057. Our parameter was 0, according to the null hypothesis. And then our SD, that's 0.156 times 0.844 over 100 plus 0.156 times 0.844 over 350. Okay. And so that's going to be about 1.385, so I'm going to round it to 1.39. All right, let's sketch a picture of a standard normal distribution. 1.39 is going to be in the right tail. Okay, remember our alternative hypothesis. We're looking for evidence of a difference greater than 0. So we're going to be shading the right tail here. And now we'll just use normal CDF to get the probability. All right, so lower bound 1.39, upper bound 9999. Okay, so the p-value is approximately 0.0823. Okay. Now, that is greater than our significance level, right? So this result is not statistically significant. We are going to fail to reject the null hypothesis. We do not have convincing evidence that the adjustment reduced the proportion of cars with the defect. All right, since 0.0823 is greater than 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that let's just use this, that the company's adjustment was successful. All right, we do not have convincing evidence that the company's adjustment was successful. All right, so all of that was part A. Now part B. Suppose that the proportion of cars with the defect was reduced by 0.10 from last year to this year. The power of the test in part A to detect this decrease is 0.72. Interpret this value. Okay. All right, let's move some of our work around. Just moving it there so that we can focus on part B. All right, so the way we interpret the power is we say if the alternative is true, and in this case, the true difference in the proportion of cars that have the defect was 0.10, okay, then there is a 0.72 probability that we would reject the null hypothesis, which in context would be to reject the claim that there was no difference in the proportion of cars. Or I think a better way of saying it is there's a 0.072 probability that we would find convincing evidence that the adjustment was successful. Right. So the power of the test is when the alternative is true and we find convincing evidence of the alternative. Yeah. Right. Part C. Other than increasing the sample sizes, identify one way of increasing the power of the test. Oh, okay, this is easy. To increase the power of the test, we could increase the significance level, right? That makes it easier to reject the null hypothesis, or makes it easier to find evidence of the alternative hypothesis.